So, hello everyone. I'm Saurav. I'm currently a PRA, Project Research Assistant at the LTS Systems Lab, IIT Bombay, working under Professor Pant. And this is a brief intro about me. I did my BTech in Aeronautical Engineering from Manipal in 2020. And during my undergraduate life, I got a research internship award from NCTU, National Jiao Tong University, which now became National Yangming Jiao Tong University, Taiwan. And after graduation, I was a visiting researcher at NUS Singapore, following which I joined full-time at IIT Bombay. And in this lab, my primary area of research relates to aerostatic lift modeling and sizing and design methodology for envelopes for your aerostats and airships alike. So continuing from what we did yesterday in this tutorial taken by Professor Pant and some of my other colleagues, I think I should start with briefly telling you the intro, that is the color scheme that we'll follow in this tutorial, because this is primarily calculation based tutorial. So first of all, I will request everyone to keep their notebook, pen, paper and calculators with them, and let me know once you have that with you. So if you guys have your calculator with you, just say it on mic that yeah, you have the calculator, you have the pen paper. I'll give you some time to gather that.
Yes, sir.
Yes, sir, we have those.
Yeah, you are ready with calculator and pen. So should we start with the intro, that is the color scheme. So since this is a interactive tutorial that involves me and you working together, we have decided this color scheme that we will follow throughout, not only in this section, but the subsequent sections as well. So the values in black will be the general instructions and the specified values. The assumed values will be in this bluish color. Then the red color followed by this pause mark will show that some calculation needs to be done by you guys, where you will do it manually with the calculator and pen. And then this navy blue color will show the final answers. Are you guys clear with the color scheme, or do you have any doubts about this?
Yes, sir, clear, sir.
Clear? Cool. Yeah. So we'll start with the motivation. So as far as I know, this was covered by my colleague yesterday. I think Nomanuddin had covered this. But in order to keep your memory afresh, I'll explain this in a brief once again. So the motivation behind this is to design a remotely controlled airship that should roughly look like somewhat an actual airship like we see in photos and videos. Of course, it should not be in some like fancy or a weird shape. It should have some payload capacity, because after all, if we have a airborne vehicle, it naturally has some payload capacity, and it should have 3-axis control. So can any one of you guys tell me what the 3-axis control is? What are the 3-axis called? Hello?
Sir, pitch, roll, and yaw axis.
Yeah, perfect. So we should be ready to control the airship along with these 3 axes possible, positive, negative. So total 6 directions. So whenever we design something, there is a problem definition that we define right at the beginning. And this is we define, of course, because there is no systematic approach available, since we work on a kind of a rare area. And the need of this design methodology is as follows. So we have to design a non-rigid indoor airship with a payload capacity of up to 250 grams. It should be electrically powered with a length less than 4 meters, and testing area should be roughly an auditorium indoor. So I'm saying that this is not like we should stick to it, but this is something that we have brought it upon ourselves so that we discipline our design to satisfy these requirements. Tomorrow, if someone has any other requirement, we'll be happy to satisfy that. But for this problem statement, we are sticking to this so as to keep all of us on the same table and get this thing trial and tested. So these are the design requirements. Now, can anyone tell me why we have mentioned this first point, that is, it should be portable and fits in a box of length by breadth by height of like 68 into 49 by 28? Just a guess. Why do you think we need to make it portable. Anyone can unmute and start. Yeah. Yeah, you can start. You can start.
So that we can easily carry it anywhere.
Yes. So if you want to test at one place, we will test it, and then we will like deflate it, fold it, and carry it to the another place. Correct?
Yes, sir.
Yeah. Quick assembly, of course, like we said, we carry it from one place to another. So we need to we need to like reassemble it in as quick as possible, right? So that's why we have kept this point like ready to fly in less than 60 minutes. It should be maneuverable, of course, in all 6 directions. I said it previously also. Pitch your role and positive and negative reduction. Typical demo arena will be auditorium, enclosed area. So you guys will be having any lecture hall, any auditorium in your college. So it should suffice that. Payload will be, the weight limit is 250 grams. Typically, a designer is not concerned about what the payload is because it can be anything. It can be cards, it can be onboard sensor, anything. As long as it is 250 grams, we are happy with it. Then volume, I think Nomanuddin has explained it yesterday that the volume 7 meter cube is typically the volume of the cylinder that we have, and we should be able to reuse that. So that's why we are keeping it with like 1/4 capacity of the cylinder, so that 4 airships would be made out of 4 airships would be inflated out of that particular cylinder. Endurance will be 15 minutes. That more than enough to demo some kind of a technology that you want to show in photo or video. LTA gas, again, we are experimenting with both of them, hydrogen and helium. The differences between hydrogen and helium is something that we will experience later when you guys start calculating stuff. And then the shape, of course, it looks like a real airship. More on the shape will be dealt with in subsequent slides. So now input data. This is extremely important as far as our today's session is concerned. So like I mentioned previously, the payload will be 250 grams. The speed is something that we have set based on the experience, that is 8 meters per second. The endurance is 15 minutes and ISA sea level conditions. So can any one of you tell me what the ISA sea level condition is? Please unmute yourself and you can tell me like what are the general parameters of ISA sea level conditions.
Sea level temperature, sea level density.
Yeah, so what is that?
It is an international standard.
Yeah, but what is the value? There must be some standard value, right? You're only saying it's standard. So what is the standard value?
Sir, about 26,000.
What 26,000?
So sea level pressure is 101325 Pascal and sea level temperature is 300 Kelvin.
300? Are you sure it's 300? You can do a quick Google search. I don't mind that.
Yes, sir. 300 Kelvin.
Are you sure it's 300? Are you sure you're not confusing between room temperature and ISA sea level standard conditions?
No, sir.
Check it again.
And sir, sea level density is 1.125 kg per meter cube.
1.125 or 1.225?
1.225, sir.
Yeah. So for our calculation, we'll use another decimal point, 1.2256. And temperature, I would ask all of you to check it again. What is the ISA sea level standard condition?
15 degree.
15 degrees. So if you
Celsius.
convert it to Kelvin, how much it will be? 273 plus 15?
288.
288. Perfect. So the ideal value is 288.16, but we are happy rounding off to 288. Okay, so everyone is clear about the input data?
Yes, sir.
Yeah. So now I'll start with the requirements. So length, as I mentioned, it should be less than 4 meters so as to look good and fit inside an adequately sized auditorium. Then volume should be less than 1.4. This comes after checking the size of the cylinder. LTA gas should be hydrogen and helium both, and tri-motor configuration. So tri-motor, can anyone tell me why we are using tri-motor? I think this was covered yesterday. So if your memory is fresh, you can tell me why tri-motor configuration is used.
Sir, one for lift, one for thrust, and the third one for the turning motion.
Lift is not the correct word. Can you say a better term?
So for controlling the lift.
I think the correct thing will be, attitude control. Basically, any
Yes, sir, yes.
direction that any direction that your airship is pointing. So this aerostatic is something that you guys have done yesterday, but I will recap it. So when the static lift is concerned, we have two main aspects of lift, that is gross lift and net lift. And the difference between them gives you the difference between gross lift and the self weight of the gas inside the envelope gives you the net lift. And in order to lift some payload, you should be concerned with the net lift. That's why we decrease the rho AV, that is the lift produced by the ambient air and the gas inside it, and the difference between that is the net lift. Now there are some factors that affect the net lift, but for this tutorial we are keeping it as simple as possible, so we are not diving into superheat, humidity, gas purity, etc. Same goes with center of buoyancy versus CG and static heaviness. So then comes design methodology. This is also explained in the past. We are using some kind of an iterative methodology that is generally used. So we start with assuming an envelope length. And so assume envelope length, we have assumed 3.5, which is like a respectable value less than 4 meters, correct? Then we start with envelope shape selection. Now this is a very important thing. So these are some of the considerations that we need to handle while choosing the envelope. So best shape, of course, gives a high lift to drag ratio. And these are the things that you do minimize or maximize. And these are the shapes that I think this was also covered yesterday. So NPL, GNVR. GNVR was again named after GNV Rao, a scientist at ISC, and NPL is National Physical Laboratory. And Shivan is kind of a new concept that is recently been published in available literature. So right now, I think we are going with a NPL shape. And if you guys know, there is also a double ellipsoid shape as well. But we are not touching that in today's session. So now we have assumed the envelope profile called as NPL. So these formulae, they might look very nasty to you, but don't worry, in this tutorial, we'll cover on how to simplify those formulae and get the values. So if you guys have any notebook, just note down this formula first. I'll give you a minute or so to copy the formula.
Saurabh, they can take a picture. They can take a picture on the phone.
Okay.
That is faster nowadays.
Fine. Okay, so should I move to the next slide if you have seen the formula?
No, let them take a picture and then say confirm to you.
Okay.
Yes, sir.
All right. So now we estimate the surface area and volume, and this is extremely important when it comes to estimating the net static lift produced by the envelope. So L equal 3.5, and for NPL profile, L by D equals 4. Now, can someone calculate D by L and tell me what the value is? Phi equals D by L.
One 1.142, sir.
What?
$1.142 is what he said.
Are you sure? If L by D is 4, then what is the inverse of L by D?
0.25.
Yes. Okay, then we'll move on to E. E is, I think, eccentricity, and that is, so you guys substitute the value and tell me what you get. To make it easier for you, I have already given you what the variable substitutions are.
Zero 0.953.
Correct. So to make our results more accurate, I'm considering up to 4 decimal places. But if you guys are accurate up to 3 or 4 decimal places, it's more than enough. Good job. The only thing is for this calculation, in order to keep everyone the same, let us follow the values that I get on screen. All right.
Yes.
Yeah. So the next is volume. Volume is pi by 6 LD square, which is pi L cube phi square by 6. So can anyone calculate that and tell me?
Zero 0.4.
Can you increase the decimal places? Like I said, 3 to 4 decimal places is something that we generally
So
dwell with.
0.4006.
Are you sure?
Sir, 1.4023.
1.402403. Correct. So now keep this volume in mind, because volume is extremely important when it comes to lift. The net lift that you calculate comes as a result of volume inside the envelope, correct?
Yes,
Yes,
sir.
Yeah, so this volume is extremely important. Then comes surface area. So this is a very nasty looking formula again, but I've made it pretty simple for you guys. So can you guys substitute and tell me what the surface area is? Is anyone up with the answer? Did anyone get the answer?
Doing so.
Yeah.
Sir, 601.688.
600. Do you think think logically. Do you think an envelope with an area of 1.4, a volume of 1.403 meter cube would have a surface area of 600?
Oh, depending on the units, now they have not mentioned the units. What are the units?
See, everything you are doing is in SI unit, so the answer will expect the answer to come in SI unit, right?
Correct.
If you are
correct.
using all meter, then the answer will be meter square. If you are using a value that is in meter cube, then the area fact the answer that the area is will be its corresponding SI unit, which is meter square. Also remember that this sine inverse, that 0.9534, it's actually radians. So make sure your calculator is on the radian mode and not on the degree mode. Sine inverse of 0.9534 radians, not degrees.
$273.06.
Again, think logically. Do you think a volume of 1.403 meter cube will have an area of over 200 meter square?
Is it 9.6498 meter square?
Let us see. No. Try again, substitute in your calculator. Let's see what you get. Use brackets properly, use sign as radians, and use fractions properly on a scientific calculator.
Sir, I'm getting answer close to 8.47, sir.
That's still not accurate.
Yes, sir.
I'll give you 2 more minutes. Try once more. Otherwise, we'll proceed further.
Yes, I got 7.7556.
Perfect. Okay, so we'll proceed further. So before touching this, I will ask you guys if you have any doubt up till what we have done till the last calculation, that is surface area.
Sir, what phi and E denotes here?
So phi is something that we call as, I think, fineness ratio, and E is eccentricity. So eccentricity is there for any what do you say? Any degree of curve, it has an eccentricity.
Yes, sir.
So since this NPL profile is also a mathematical curve, it also has an eccentricity.
Okay, sir.
Okay, any more doubts? If you have any general concept also, it's fine, like not particularly related to the values also. Or should we proceed further?
Yes, sir.
Yes,
Yeah.
sir.
So now remember this volume, remember this surface area. Okay, volume being the most important thing. So some people who have actually worked on airship, including our lab, some people from Germany, some people from China, some people from US, they tested various airships and they found this particular graph as a trend line. So this black line is a trend line and the individual units are the core values of what the study has done. And if you observe, this trend line gives a relationship between the payload and the volume. So if we put our payload as 250 gram, that is 0.25 kg, what volume will get using this formula? This is fairly easy. So you guys can do it now itself on calculator and tell me what the value you get for the volume.
Two point six six three.
2.663.
2.66, correct. So now can anyone tell me why this volume is 2.66 and why the actual mathematical formula that we use gives 1.403? Can tell me why this is such a difference? Have a look at this graph and tell me why there is this deviation from the mathematical value. Feel free to unmute yourself and talk.
Speed changes.
But how will speed relate to volume? If you have a car and if you have a truck, both run at 60 kilometer per hour, but truck volume is more than car, right?
Yes, sir.
So see, look at this graph, study this graph and tell me why we have a difference in the value obtained from this graph and the value obtained from actual mathematical calculation for the NPL profile. You can make an educated guess, no problem.
Because of shape.
By discharge formula.
Because of
The shape.
I'm not able to hear. Because of
Because of different shape.
but different shape. See, this is an empirical relationship. So a standard airship shape for a particular payload will roughly be the same, right? It should not deviate almost double of it, right?
Due to area.
But area is coming out of the fabric that you cut, right? So if volume is more, then area will be more. If volume is less, then area is less. This formula says nothing about the area. See, I will give you one small exercise. You guys have your laptop, PC, mobile, right? Can you search any of this for 3-4 blimps? Just have a quick Google search.
So we have a discharge formula Q is equal to AV from that.
What?
So discharge formula Q is equal to AV.
So how does discharge formula come into picture?
So as area is increasing, our velocity also increases.
Area and velocity, are you sure?
Yes, sir.
Okay, I will give you one small exercise. Just search any of the names. You can see the names in the list on the right, right? Just
Saurabh, they
search.
don't need to search. They just need to look at the y-axis and apply their mind. Yeah, they no need to search. Look at the y-axis, apply your mind, and answer the question: why is the volume coming much more than what you are expecting?
Due to payload increasing.
That is what the graph says. But if you see here also, 250-gram payload, where does 250-gram payload lie? It lies here, right?
Yes, sir.
So see the size of the entire graph and see the place where the 250-gram payload is. That's why I asked you to search any of these. If you observe, these are blimps are huge blimps. So the empirical relationship that comes out of experiments and testing will be biased towards a bigger size. This is why we are having such a huge range in this graph. And if you see if you see payload, what is the maximum limit that we have? 20-25 kg. See the volume in this gram. What's the limit? 50-60 meter cube. And whereas our payload is like a fraction of it. 250 gram is like it can't even be shown on the y-axis, right?
Yes, sir.
So this is the reason why we go with mathematical calculation, because empirical formulae always relate to things of similar class. So
Yes,
this particular relation is after comparing lots of very big airships, and we cannot just simply take the values biased on this airship and say, "Ki ha, I can make a small airship." For small airship, you need to have design and testing zones pertaining to the small airship, and this is why we go with dedicated mathematical formula. Correct? Now, a similar study has also been done by a person called Young, who studied R101 class of airships, and he defined, out of his experience, he defined certain area and volume, and area factor and volume factor for those airships. Again, these are empirical data, so they are biased towards large airships, and this is what they found. So again, if you see the length is like 10 meter, 20 meter, it's running. And these are also for very huge airships. Same goes with this. Very huge airships again. So this is why we shouldn't bias our results towards what is already available, unless what is already available matches what we want to do. If you want to design a big airship, then you can see the results and comparative study for big airships. But that is why in slide number 2 or 3, we have already written that no such methodology is present, because for small airships, no one has done such a kind of a comparison. Correct? You read this one sentence, right? That the motivation behind is that no such methodology is present. Do you remember?
Yes, sir.
Yeah. So this is the reason. And so now we come to the final part of this particular tutorial, that is aerostatic lift estimation using the values that you got. So before proceeding towards actually finding the values, can someone tell me, if you are designing an airship, what would you do from this step onwards? You have the area value with you, you have the volume with you. How will you calculate now? You can do a quick recap to what we had done yesterday and what I had told you like some 10-20 minutes back maybe. How will you utilize those values? You can make a guess again, not a problem.
With the help of area and volume, we can find surface area.
Area is surface area, right?
Okay, sir.
Okay, let's say I tell you ignore area, keep only volume. Then how will you calculate?
That formula pi by 6 LD square.
But no, that is for volume. I am telling you the volume is there. And now how will you calculate lift out of that volume? If you are a designer, how will you calculate lift out of the given volume? Okay, now before that, just tell me what makes an airship or an aerostat lift itself? What is the reason?
Sir, the gas present inside it.
Exactly. So can you rename the gas that we are trying out with? There are two gases that I mentioned.
Hydrogen and helium.
Helium and hydrogen.
So now this volume that you guys calculated 2 slides back, what volume do you think that is?
That is the volume which will be occupied by the gases.
Correct. It will be occupied by the gases. So now, what is the contributing factor towards production of lift? There is one factor is volume. What's the another factor? What makes hydrogen and helium so special as compared to air?
So they are lighter than air gases.
So when we say the word lighter, what does it denote scientifically?
They have less density.
Perfect. So the keyword is density. Correct. So now you have two keywords before you. One is volume, one is density. Now tell me, how will you play with these two keywords to get the lift?
Density is equal to mass upon volume.
Okay, but density is already there. And density is already there, volume is already known. Correct?
Yes, sir.
So how will you find the self weight now? Mass equals?
Rho V.
Rho V, correct. So one factor will be rho V, that is density of the gas inside and the volume. Correct. But some slides back, I had told that there is one thing called as net lift and there is another thing called as gross lift. Correct?
Yes, sir.
So how will you calculate gross lift? What other density you know except the gas?
Sir,
Air density.
rho A,
Air,
ambient air.
correct. And can someone repeat the value in standard atmosphere?
1.225
Correct.
G per meter.
So now you have density of air, that is 1.225, and then you have density of a gas that is lighter than air. Correct?
Yes, sir.
So that density will be naturally lesser. Am I right?
Yes, sir.
Yes.
So if in order to calculate the lift, what should be subtracted from what?
Density of air subtracted from density of gas.
How will you subtract a bigger value from a smaller value? Then that will give negative, right?
Sir,
Just
we
think,
have to find net lift now.
yeah, so to find the net lift, see the formula that I had told some slides back.
Vg rho of air minus rho of Lg.
Yeah, so rho of air minus, so bigger value minus smaller value, correct?
Yes,
So
sir.
always remember that the lift force that any envelope with LTA gas inside it generates is as a result of the difference in density between the ambient air and the gas inside it. Correct? Multiplied by the volume, of course, to find the weight, force. So force is essentially the lift. Correct?
Yes, sir.
Okay. So now we will proceed with the final topic of this session. We have 8 minutes remaining. So we know the envelope volume. Remember that this is from the calculated values from the envelope profile. Then we have density of ambient air that we are considering 1.2256. Again, 4 decimal places to maintain some accuracy. Now we have one gas, that is hydrogen. So let us proceed with hydrogen. So this is the density of hydrogen, 0.0841. And so this is lifting capacity. So can someone tell me how did we arrive at this value of 1.1415? And we called it as lifting capacity. This value is not coming from magic, right? There is some derivation for this particular value, 1.1415. So can someone tell me how did we get this?
By rho Ag formula.
See, rho Ag.
So
Is it
rho of air into area into G.
Why would you involve area now? The lift is produced only by the volume, right? See, I will.
1.56 plus 0.0841. That
Correct.
is
Correct.
density.
Correct. So again, I am telling you again and again that the lift produced by any envelope with LTA gas is as a result of the difference in density between the ambient air and the gas inside it. So that's simple. Ambient air density is known, gas density is known. Just subtract, so that effective value will be what is producing the lift, right? And this is why we call this as lifting capacity. Correct. So all you have to do to find lift. So now as someone said that a density equals mass upon volume. So let's consider this mass as a force. So now this lifting capacity is the difference in density. What will you multiply it with to get that force?
So can you repeat?
This, we have the density with us, we have volume with us, we have surface area with us, we have the values required. So now what values you would use to get the net lift?
Density, volume, and area.
Yeah, but I had told you can ignore area. So see, if density equals mass upon volume, then what does mass equal?
Rho into V.
So we have the effective rho that is producing the lift, correct?
Yes, sir.
So now multiply it with V, simple.
Yes, sir.
We know the volume, so try multiplying it.
1.601.
Yeah, 1.601, 602, same thing. So now
Yes.
can you do the same for helium? So now we are going to helium, and this is the gas density of helium, 0.1662. So can someone tell me what the lifting capacity is for helium? Just subtract the values.
So 1.054.
1.0594, yeah.
9.
Then again, what's the net lift that you get by multiplying the values?
One 1.486.
1.486. So now we have what lift the envelope will produce if you have hydrogen inside it and if you have helium inside it. Now tell me, why is hydrogen lift more than helium's lift?
Sir, because it has less gas density.
Then
because
why is
hydrogen
hydrogen so
power
now this
that
is a scientific term, correct? But now if you want to tell to a normal person that hydrogen produces more lift than helium, how will you say it?
Hydrogen is light.
Yes,
than helium.
correct. Hydrogen is lighter than helium. This is the simplest term, correct?
yes, sir.
Okay, so now you have air, then you have helium that is lighter than air, and then you have hydrogen that is even lighter than helium, correct?
Yes, sir.
Yes, sir.
And this is the reason why hydrogen and helium are considered as decent or like very good LTA gases, because they are lighter than air. Can you give me an example of another such lighter than air gas?
Nitrogen plus oxygen.
No. Any lighter than air?
Methane.
Methane. Let me check the density of methane.
That's correct. Correct. Methane is
Yeah,
like
methane is one of them. I think argon is also one of them.
yeah, many noble gases are there.
Yeah, argon is also one of them.
Neon.
But now my last question in this session will be, if you want to make an LTA system and someone tells you to not use any LTA gas, use only air, how will you do it? This is my last question to all of you.
Hot air.
Hot air balloon.
Perfect. And this is the reason why hot air balloon exists, is that the density of hot air as we heat it is less than the density of ambient air, which causes that lifting capacity and that lifts it up. So this marks the end of our presentation, end of our tutorial for calculating the net lift. And I think we are exactly 11:50 now, 49. So I can answer a few questions if you have, or we might go for our 10-minute break. I think Professor Pant can comment on that.
Yeah, so what we will do is we will have a 10-minute break. But if somebody doesn't want to take a break and ask questions, we have no problem.
Yes. So anyone wants to leave for a quick snack break, they can.
Yeah, go ahead. We will start only at 12.
Yeah. If anyone wants to talk to me, discuss with me on whatever we have covered till now, feel free to do so.
So,
Yes.
so we are not aware of Young's area factor and Young's volume factor. Can you define it, please?
See, you are not asked to be aware of that. This is something that a person has done based on the tests on various big airships. And he has found these values. This
Sir,
is
but
this.
what is meant by Young's area factor and Young's volume factor?
Okay, now how can I say it? It essentially is something that relates the area. That's it.
Let me try to explain, Saurabh. So, Saurabh,
Yeah.
there was a scientist called Young. He studied many airships, different airships. He plotted their areas and calculated the volumes. And then he found a correlation between the diameter, length, area and volume by giving these equations. So that is why we call it as Young's area factor and Young's volume factor. Basically, it says that if you have an airship with diameter d and length L, the area will be roughly 2.33 times d into L. If you have an airship with diameter d and length L, the volume will be 0.465 times d square into L. That's all. That is what it is.
Okay, sir.
Okay, sir.